So here is the topic. It is application of automata theory in game theory. So we are going to discuss this entire topic into two sessions. That is, first is the game theory, and second is the automata, how we can implement the automata inside the game theory. Talking about the game theory, the study of decision-making the scenarios where the action of multiple individuals or players determine the outcome is known as game theory. An interdisciplinary field of mathematics and economics. It is applied to stimulate the situations where strategic choices are made by the players to achieve their goals while taking into account the decisions made by others. The concept of rational decision-making formed the basis of heavily economic behavior models developed by mathematicians like John von Neumann and Oscar Mostrom in early 90s. Over the time, the game theory has emerged as a widely used tool in various fields such as political science, psychology, and computer science economics. In the forthcoming slides, we are going to talk about what is the evolving fields we can implement this game theory with an automata. The study of game theory involves the examining of formal models of strategic interactions between players. These models are called games, consisting of a group of players, a range of actions each player can take, and set of results that can differ based on the action taken. It is assumed that players in these games are rational and motivated by self-interest, always choosing the option that leads to the most favorable outcome of the, for themselves. Basically what it is, actually we are having some entities in a game. What we can manufacture is in game we are having some characters. So this interaction between the characters or interaction between the entities, we call it as a game theory. So what is the need of the automata here? So when we are telling about a game, there are some characters. The characters will do some work. In terms of what means, they will decide something, or they will take some decision. According to the decision, they will get to pay the payoff. So the decision will be characterized, or the decision will be manufactured in terms of automata. So that is the thing we are going to talk about in the entire sections, that how the decision can be influenced by the use of the automatas. So talking about, so in the game theory, what is the main entities that is being represented in a game? So basically, we have divided the entities into three parts. That is our players, strategies, and playoffs. It is the three major entities in a game theory. So apart from that, we can more and less we can derive some other entities also. That is going to see in the forthcoming slides. So talking about what is a player in a game theory, a player refers to an entity or individual that participates in a strategic interaction. Players are regarded as rational and self-interested, which means they aim to select the action that provides the most favorable outcomes for themselves. So what it is feeling in a game theory, or whatever you call it, in game or something, the player is is an individual entity. So what it will tell, so what it will do, so they have their interaction with the other players. Like we know in the simple games what we are doing, we are entering as a character and we are having some other characters, so we are interacting with them. So these are actually the players. What you call it as an entity player. So what is the strategy? The strategy is a course of action that a player can choose in a game. Each player has a range of potential strategies and must select one of them to play a game. Strategies can be uncomplicated or complicated, or many encompass a variety of possible actions. So we are talking about strategies. So this is not dynamic here. There is we have to choose a particular strategy based on some strategies. So we don't have something that we can choose any of that what we want. Apart from that, we are having some sort of strategies. So among the strategies, we have to choose some strategies, and according to that, we have to move on. So that is the thing that this strategy, so this choosing process we can do based on the automatas. So this then comes the payoff. So what is the payoff? Actually, what we are doing, what is the outcome of that strategy? Or suppose we are in a level now. In that level, we choose to move in a particular path. After we enter to the path, what is the next surface, or what is the next level game, or what is the next outcome that will come for us? It is characterized as payoff. So there is a thing that payoff is telling. The payoff is the outcome that a player attains as a result of their selected strategy, and the strategies adopted by the players. Payoffs can be positive, negative, and are frequently assessed in terms of players' utility and satisfaction. So now, apart from the three major components of the games theory, we can categorize it as some derived categories such as Nash equilibrium, dominant strategy, and mixed strategy. So talking about what is a Nash equilibrium, the Nash equilibrium is a concept that explains a situation where each player selects the best strategy based on the strategies proved by the other players. That implies that no player can achieve a better result by changing their strategy without assuming that other players will do the same. So, so this is the thing we can understand by a suitable example. Suppose we are having A and B. They are running two businesses, vying out for market share in a certain sector. They have the option for advertising or not. The following in the game's payout methods. Suppose B advertise and A doesn't advertise, or A advertise, B doesn't advertise. Both A and B are advertising. So we are having a scenario here. So what is happening here? Depending on the decision each firm makes, each number in the matrix indicates the reward for the company. As an illustration, if A advertises and B doesn't, then A makes a profit of 3 and B makes a profit of 0. When both business decided to advertise, the game reaches the Nash equilibrium, which you can see that A and B both are advertising and they are getting the profit of 2 and 2. So this is even situation of Nash equilibrium. If A advertises, B doesn't advertise, A will make no money and would much rather stop advertising. B advertise, A doesn't advertise, B will benefit by 3 and would rather stop promoting. The only predictable result is that both business will advertise. So what it is telling, that suppose A is advertising, or B is not advertising, but A will get the maximum profit in 3 and B will get 0. So and over the course of time, A will stop his promotion. And same goes for B, B will do the same. And so the only predictable result we can predict that they both will run their advertising. So that's the next equilibrium motif, which is telling that decision concept that explains a situation where each player selects the best strategy based on their strategies chosen by the other players. The implies that no other player can achieve a better result by changing their strategy without assuming that the other players will do the same. Talking about the second thing, that is the dominant strategy. Dominant strategy refers to a player's best choice irrespective of other player's strategy. If a player has the dominant strategy, they will always choose it to maximize their payoff. Suppose the thing we can give an example and we can understand this properly. That we are suppose we are having a game and we are in a game and we are suppose in a label in that label. So talking about any political issues or any economical issues. So suppose we are having a political survey is going on. So what you can tell here that suppose a person is looking for an votes and something. So we don't have to see on the other participants votes and something other stuff. So what we can see there that our base is irrespective of the other strategies. That is called as the dominant strategy. And mixed strategies, on the other hand, involves the element of randomness, such as flipping coin to decide between possible actions. This strategy can be used to ensure that other players can predict a player's action. So these are the strategies, or these are the basic concepts of game theory and the derived concepts of the game theory. So talking about like how many types of games we can have. So game theory classifies games into different types based on their characteristics and rules. Here are some most common types of games that follows is simultaneous games, sequential games, and non-zero sum games, zero sum games, and we can add up something like cooperative games and non-cooperative games. So we'll talk about later. We'll talk about what is the cooperative games and non-cooperative games. So first, let's jump into simultaneous games. So what is the simultaneous games? Players choose their strategy simultaneously in the kind of game without being aware the decision made by the other players. So same with that we have seen in the uh, dominant strategy. The players will choose their strategy simultaneously in this kind of game without being aware what is the other person is choosing. The prisoner's dilemma and the battle of the sexes are the two examples of concurrent games. Talking about sequential games, players select their plan sequentially in the form of game. Each player selecting a choice after considering the decision of other players before them. So that is totally different from the simultaneous games. So what is happening in the simultaneous game? The player is choosing something without the knowledge of what the other player is choosing. But in the sequential games, we can tell that the player is choosing some strategy based on the strategy of the other players. So we can give the example of chess and stuff and poker. We can tell also, and some extent poker is also right. The player will play their next move based on the move of the other person. Talking about zero sum games, basically the poker games that all of the gambling games comes under this category. The player's gain in zero sum game is exactly offset by the another player's loss. In other words, the player's loss never add up to anything. The majority of gambling games, including blackjack, roulette, are examples of zero sum games. Suppose we are having the 4 to 5 years, yes, we are playing a poker game, each having contribution of $100. So suppose the person wins, means he will get the entire money. Where here, no one will add up something, or no one will like apart from the person who wins, he will get the profit. Rest of the person, they will get the loss, but there is nothing that can add up our players. So talking about non-zero sum games. So basically, this non-zero sum game, you can imagine a scenario like a von Neumann diagram, like a Venn diagram. What is happening there? Suppose we are having A as an entity, B as an entity, and we are having total A set, B set, and A intersection B set. So what the A set does? A set tells about the interest of win of A. The B set tells the interest of loss of the other person, and the A B tells about the win-win scenario. So that can be fully implemented in the non-zero sum games. If you can see what is that briefly. The sum of players in a non-zero sum game can be either positive, negative, or zero. In cooperative non-zero games, participants cooperate to accomplish a shared goal, while in non-cooperative non-zero sum games, players compete with one another. Prisoner's dilemma and ultimate of game are that's the thing we are talking about in this slide. That is the cooperative games and non-cooperative games. So what is happening here? It will briefly tell about what is happening in the cooperative games. That we are having some characters. They can cooperate with each other to accomplish a goal. So based on that, they will get their merit points or their rewards. Suppose a person who will not cooperate with the another person and will simply accomplish his goal, one goal without of any cooperation, then he will get some reward. As well as some of the negative points, he will get some negative points also. Same goes for the other person. If they will cooperate, then both of them they will get the rewards. The contrary of the non-cooperative games, what happens here? Both of the players, they don't have to cooperate, they have to simply accomplish their own goal. Based on that, they will get their rewards. If they will cooperate, means some points will be deducted from their games. So there is the entire wholesome idea about what is the game or how we can characterize the game based on their characteristics and the rules. So now we have just seen an overview of what is in game theory. So if you sum it up, like what is in game theory? So game theory basically we are having some environment. In that environment, we are having some characters. They will interact with each other. They will interact with each other. They will take some action, or they will decide something based on some we are having some strategies, and based on their strategies, they will decide some strategy and they will go to the next step, or they will face the payoffs. So that is the thing that is all the entire scheme. And to read all the patents or to study about everything, we call it is a game theory. And automata is there. The decision making process, it can be enhanced by the help of that automata. So now let's jump to what is an automata and game theory, how the automata can influence the game theory. So before starting, let's see. We are having three types of automata here. There is the finite automata, adaptive automata, and cellular automata. So then the finite automata, that is in the first 90s, if I'm not wrong, that in 1985, that the starting he started working on the finite automata. So based on from the year like in early 90s, we started working on the finite automatas in the during the year of 2005 or 2006. Then we jumped to adaptive automata. It's not like we are not using the finite automatas now. We are still using the finite automatas, but see what is the difference? What is the main problem between finite automata and adaptive automata? The finite automata is applied to the simple games, which where we can predict something like some simple scenarios we can predict. More or less, adaptive automatas is something different compared to the efficiencies. Adaptive automatas is slight efficient. The cellular automata, both heads of their shortcomings, which can be compiled by cellular automata. But the cellular automata for that now the currently research is going on. It's not now fully complete. So currently the work is going on for that. So in this topic we simply discuss about the finite automata and adaptive automata. Cellular automata will not discuss in this topic because currently work is going on there. So we don't have specific wholesome knowledge about that. So we'll discuss about finite automata and adaptive automata. So we'll give an example. In database systems, when we are previously we are using our main motto is for the redundant data because of the memory constraints or because of the memory constraints because we don't have enough space or the prices are more. But when these concepts are introduced and memory becomes cheap, then we suddenly transfer from redundant data to more speed and stuff. So same thing applies here. By the time when we see that we are first applying the finite automatas, but when we see that finite automatas can no longer meet our requirements, and we see that adaptive automatas can be compromised and adaptive automatas, all the operations in adaptive automata that can be completed in a very less or in a very cheap price, so it transferred to adaptive automata. So let's jump into automata and game theory. We'll briefly discuss like what is automata and game theory, how we can apply it with an example. We will see what is the shortcomings and what is the future stuff and rest the conclusion. So talking about automata and game theory, automata can be very useful in game theory, particularly in analysis of games where the strategies for participants are interconnected. Systems that are very time can be represented mathematically using automata. The strategies and choices made by the players in a game are represented by automata in game theory. Automata learning has grown in significance as a tool in game theory, especially when it comes to using machine learning algorithms to understand the tactics of other players. Process of automatically then determining a model of system's behavior from the observable inputs and outputs is known as automata learning. By the examples their previous conduct in predicting the future behavior, automation learning in game theory can be used to learn the strategies of other players in a game. That is the thing we have discussed previously. This telling about this in this there is a major point here that by the over the course of time when we are talking about that we are having players who are deciding actually what which of the strategy we have to select. They are self-motivated or they are not influenced by something. We are having some sort of strategies and they have to choose based on the strategies, but they are self-motivated on their own knowledge only. They have to choose. So there's a complete fact this is telling. So let's see this game that can be modified with automata include the qualities. Some of the games we will see just examples of there are lots of examples, so there are numerous examples that is can be applied with automata. So we have just listed 3 to 4 examples just to get an overview of how games that can be modeled with automata will be useful for us. So talking about the first example, that is prisoner's dilemma. So what is happening in the prisoner's dilemma? Two players must choose whether to collaborate or defect in this classic game or game theory. Both participants will receive a little reward if they work together. The defector obtains a great prize, and the cooperator receives nothing if one player cooperates, while the other deviates. If both of the players cheat, they are both subject to a life penalty. An automation with 2 players can be used to stimulate this game, with each player having the option to collaborate or defect. So that is the idea of this film. Same like cooperative stuff. One player is to cooperate with another player, so they will get some prize. If they will both debate them, they will get some penalty. So we can manufacture automation with the 2 players. So within 2 players schema, we can manufacture the finite automata here. So talking about the chicken game, in this game, what you can do is the 2 players are dividing towards each other. So sorry, the 2 players are driving towards each other, and both must decide whether to swerve or continue driving straight ahead. If both players swerve, there is no collision, and they both receive a small reward. If one swerves and the other doesn't, the other player who doesn't swerve receives a large reward. The other swerve receives a small punishment. If both of the continue driving straight ahead and there is a collision, both will receive a last punishment. This can be modeled using a 2-layer automation where each player has 2 strategies: swap or continue straight ahead. Same like prisoner's dilemma. What you can do, we have 2 entities here. We have to choose based on we are having some schema. The schemas are we are having some we are having 2 schemas here. That is either you have to swap or you have to go straight. So based on the schemas, what they will choose, they will get their reward. So you can characterize it based on a finite automata. So this is a simple game what we are talking about. Talking about the third game, that is the matching tennis. What is that? The head or tails outcome of a penny is selected by 2 players simultaneously in this game. One player wins and the other player loses. If both players display the same force, if players' faces vary, then other player prevails. A 2-player automation that allows each player to choose between showing heads or showing tails can be used to mimic this game. Same like previous examples, it's a simple game we can do in the finite automata. But in ultimate game, a participant in this game can accept or reject another player's offer to divide a sum of money between them. The recommended division of the funds occur if the offer is accepted. Both the players gain nothing if the offer is turned down. A 2-player automation that allows each other to choose between making a high or low offer can be used to mimic this game. The same thing, like previously, we all are the same examples between the 2 entities. So what is selling about the ultimate game? So they are having some money. They want to distribute if they both agree. So they will, in that case scenario, they will get they will both get some points. If they will not decide if they don't want to divide, they will both turn down the offer. Then they will get nothing. So based on that, this is an automata you can design for both of them. So talking about what is the application of finite state machines in game theory. So here comes the topic like how we can apply the finite state machines in game theory. So this is the application part, and after that we will see that how actually we can apply this finite state machine or finite automata in the game theory. In game theory, finite automatas are computed to simulate clear action and strategy. The inputs reflect the actions the player can do in each state. The states of the finite automata indicate the various possible game situations. The transition function specifies the outcomes that follow from each combination of player actions and establishes the game rules. The game theorists can forecast the game results and pinpoint the best player for each of the player by examining the finite automata's behavior. So simply what it is telling, we are having the entities and they will have some sort of rules. So we are having the game analyst. So what they will do based on the rules of the game, they will decide their action and they will give the reward or whatever it may be, the winning situation or lose situation or both, or until and unless both of the situation can win. So what is that? We can characterize it into the three types. That is the sequential games, repeated games, and evolutionary games. So in sequential games, what it happens is finite automata models with each state representing a game state in transition defining possible actions or outcomes. Game theorists predict the optimal strategies. So simply it is telling. So we are having a space, and we can predict based on the strategies. We can predict the same space. So we are having the theories. We can predict the optimal state strategies for that. Based on the choice, we can get the reward. Repeated games, what happens in the repeated games? A finite automata models repeated games with space representing the game history and transition defining possible actions. Game theories predict the optimal strategies for player over the entire game sequence. And the evolutionary games, finite automata models, its states representing the current strategy distribution and transition defining the probability of adopting new strategies. Game theories predict long-term outcomes and identifying the surrounding strategies. So this is a simple thing we can just go through and can just learn it. So this is the important part. So we see like how in finite automata works in examples, works in the real life scenario. So here we have taken the example of an N-player privilege dilemma. So as we all know that the finite automata can be defined as that R, and it is being represented by four symbols, which is S, I, F, and S naught, where the S is the set of states, I is the input symbol, F is S into F equal to S into Y equal to S. That is the transition function in all of the automatas. We have seen that there is some sort of transition function. So here F is the transition function, and S naught is the initial state. So what is happening here? For the instance, we in the iterated n-pair privilege dilemma, the finite automata can be used to represent clear strategies. The automata states or the represents the player action, and the input is the strategy profile observed from the other players. So what is happening here? We are having the C1 as the initial state. We can tell the C as the initial state. If this round none of the other two players play, then we can definitely we can call it as C, and the total number of cooperator will be zero, excluding the player itself. Transition zero will change the current state from C1 to D1. In the following round, the agent will play D since the current state is D1. And assume that one player is cooperator, therefore the total number of cooperator will be 1. The transition 1 changes the state from D1 to D1 itself. In the next round, the player will play D again. However, using finite automata as a modeling language has its own limitation. Finite automata are only capable to recognize the regular languages. In other words, it is possible to guarantee arrival of a specific state only for a determined class of input sequences. As we all know, that the finite automata can only be characterized for the regular languages. Suppose we are having the scenario that where the language is not regular, or we are having some different, like we know that we can have context-free languages, can use the context-free grammars or put down automatas here. So finite automata will be limited up to some stage, like for the regular languages only. So after that, we'll introduce the put down automata, which is the context-free grammar, how we can implement that, and based on that, what is the limitations of that. After that, we'll go to the adaptive automata. So let's jump into the modeling of games with context-free grammars. So suppose we are taking the example of a poker game here. The game of poker is one of the example of a game which can be modeled using put-down automata. Each poker players receive a hand of cards based on the situation of their hand and the cards on the table. They place bets. The beginning state of the game is the hand cards to deal with each player. Each succeeding state is the outcome the players actions, which can be visualized as in context-free grammar. The game of name is another illustration where game may be modeled with the put-down automata. Where each player in the game name takes turns taking objects out of the various object piles. The piles arrangement can be thought of in games beginning state, and each succeeding state is the outcome of the player's action in a context-free grammar. The PDA can be successful, that is, the put-down automata can be helpful in the game theory because they can employ context-free grammars to capture the recursive structure of games, the intricacy of the game, the base planning styles for each participant, the game's potential outcomes can all be discovered by the researchers by examining the PDA. The put-down automata can also be used to stimulate the games, enabling researchers to evaluate various practice and game configurations. So this is the thing that is telling. We previously seen that we are using the finite automata, and what is the problem in the finite automata? We are only accepting the regular languages. So to come through this problem, we introduced the push-down automata, which can model the context-free grammar. So the push-down automata can be really helpful in the game theory because it can employ the context-free grammars to capture the recursive structure of the games. So based on that, so what is the help you can get from mobile? So this is about all about it. We are telling about how the context-free grammars can overcome the shortcomings that regular language accepting finite automata. So let's jump into the applications of adaptive automata. Like we have already told that how adaptive automatas are introduced in this context. Why we switch from a regular automata to adaptive automata in previous sections. So telling about what is the main perspective here, what is the main advantages here? Adaptive automata had cheaper implementations compared to the other mechanisms. That's why, in the sense of cost, we transform from the regular automata to the adaptive automatas. So the adaptive automatas used by the device have been presented as powerful tools for defining the complex languages. Adaptive automata has the following important features. That is, accepting procedure performed by an adaptive automata is done efficiently due to the structure which is based on the finite state or the structure push-down automata. Adaptive automata can handle context dependencies in a strict syntactical way without the aid of auxiliary semantic procedures. The structure of adaptive automata can be extended into the implementation of transducers along the generation of parse trees as a side effect of parsing sentences. Adaptive automata can be considered as an alternative to existing solution of natural languages processing. So there is the thing it is telling about it. Basically, adaptive automata is an extension of push-down automata because we are using the context language with the push-down automatas. So these are the factors we have with adaptive automatas. So it's an already existing solution. Like we are having the natural language processing. We are having the solution for that is the finite automata. So it's a solution to already existing solution because it's not truly defining the forthcomings of or the shortcomings of the finite state automata, but it actually provides a better solution compared to the finite state automata. So we are having the cellular automatas which can completely apply or we can completely fulfill the shortcomings of the finite state automata and the adaptive automata. But we are now under the process. Now the researchers are they are doing their research on that topic. So in this sections, we are not going to talk about the cellular automatas. So now talking about so what is the automata learning in game theory? So this is like briefly we are telling about previously in the section we can go on how this automata and game theory can be adapted to different sections. So majorly you can give the example of three sections here. It is the economic section, political section, artificial intelligence section. How it can modify it into these sections and apply it into it. So what it is telling, game theory and automatas are very effective tools with many diverse applications. Researchers and practitioners may model and analyze computer systems, create effective algorithms, and learn how people and groups behave in various settings by using these tools. So in economic section, how we can help, you can see that economic makes considerable use of game theory to stimulate and examine choice made in conditions of competition. Understanding different economic phenomena, including market behavior, pricing tactics, and the effects of changing policies on the market can be guided by game theory, supply chains, financial markets, and transportation system may all be modeled and virtually tested using automated theory. So basically, it is telling like how an economic way can be held and can be implemented in this sense. So same thing about the political science and the artificial intelligence, how it can be moved into it. We can previously we have given the example of political science. This isn't just adaptation or this isn't just extension of that stuff. When talking about the artificial intelligence, the theory and design of computer algorithms and artificial intelligence are fundamentally influenced by the automata theory. And with the introduction of the machine learning, it can be enlarged and greatly enhanced. So talking about the future direction, what is the future direction we are having? So we like lots of future directions that we are having. So we just included 3 to 4 scopes here. So talking about that, first is the new modeling techniques. Automata and game theory are being used as increasingly frequent by researchers to stimulate and evaluate complicated systems. For instance, scientists are investigating the use of probabilistic automata to describe the stochastic and the uncertain systems. So that's how the new modeling techniques you can introduce the practical applications, the multi-agent systems, the complexity and scalability. These are the factors that we can variously work upon in the future direction. On the future domains, we can get the great help in these directions. So in the overall, we shall tell that we talked about this two sections. First is what is the game theory, how the game theory and how it exists. And secondly, we talked about like how we can apply the automata into it and how it can help us in our process to be smooth and using game theory and automata the automata. In different sections, how we can use it in the previous slides, we have seen it. In the conclusion, what we can tell is that game theory and automata are significant disciplines of research with numerous applications. Game theory studies how strategic decisions are made in competitive circumstances, whereas the automata theory studies the mathematical models, computing and communication. Together, these disciplines are strong tools for stimulating and analyzing complicated systems, creating effective algorithms, and learning about how people behave in various situations. Several fields, and including economics and political science and engineering and artificial intelligence, use automata and game theory. The process will be smoother and our life will be the forthcoming life will be greatly affected by this. Thank you.